Yeah, I think there's no more. I got bugs and folks.
Hello guys, I guess we can get started. Today, it's our pleasure to have special guest. Today is ICOM Distinguished Seminar with our speaker, Professor Ed Colgate from Northwest. I want to start a little bit kind of robotics a little bit background here. So robotics has like 70 years history. Early days, they are deployed in industrial factory. They do welding, assembly tasks, but they are physically isolated from human. You have a fence, light curtain to isolate the human from the robots because they are dangerous. They may hurt human. Recently, people try to bring robots to human shared environment, collaborate with human. So the safety becomes very important issue, right? And 1996, Professor Colgate and his collaborator Michael they developed the first terminology of collaborative robots. That's how these collaborative robots come to your lab space. UR5, most people use that. Kuka Eva, Panda Franca, all these collaborative robots now, you do not need a physical kind of fence isolated from the human. You can just collaborate with the robots in a shared space. So yeah, Dr. Colgate is the inventor of the technology collaborative robots 30 years ago. I want to add a little bit more introduction. He's a professor from Northwest, and he's worked on haptics and also manipulation. He's a fellow of the National Academy of Engineering, and he's a member of National Academy of Engineering and a fellow of National Academies of Innovator. And he is also a fellow of HB, and he is also the co-director for the National Science Foundation ERC HAND. It's called Human Augmentation While Dexterity. It's $52 million program, 10 years from National Science Foundation. So clearly, Dr. Colgate needs to make a big contribution and a huge impact to our community. Without further ado, let's welcome Colgate. Floor is yours.
Thank you, Professor Chief, for that really nice introduction. When you start by saying 70 years ago, I was afraid you were going to say that's kind of when my career began. Almost. Yeah. So, but I'm really happy to be here. I've been to Purdue a few times over a long career, and every time I come, it's a more beautiful, more developed, more exciting place to be. Today, just had some really wonderful conversations about the great things that are happening here. So today, I want to talk to you about work that we've been doing on tactile realism, subtitle Human Resolution Haptics, and that'll make more sense a little later on. I do want to say just a little bit more about me and really kind of where I'm from. I have been in the Northwestern faculty for over 37 years, and in that time, I've mainly worked in this area of haptic interface that I'll talk about today. I'm doing some kind of different things these days I'll just allude to. I'm a part of our Center for Robotics and Biosystems. We've got about 12 core faculty and a number of others. We work on everything from swarms to manipulation, soft robotics, rehabilitation. And so check us out, robotics.northwestern.edu. There's a lot of really exciting things happening in this lab. These days, my life is really mainly dominated by the center, as Professor Sheet mentioned. Starting from September of 24, we've been leading NSF Engineering Research Center. So these things are pretty large. They're funded, as you said, for like $52 million over a decade, and involve multiple universities. These are all the ones that are part of our center. Carnegie Mellon, Florida A&M, Northwestern, MIT, and Texas A&M are core partners. All of us have at least 4 faculty and at least 4 grad students involved. And we're all about dexterity. We are really trying to move toward a future in which robotic manipulation is intelligent, dexterous, versatile. But really critically, this idea of making it accessible, widely accessible, especially to small manufacturing firms. If you look across this country today, you'll find that the adoption of robots is really concentrated in larger firms, the auto companies, the Amazons of the world, and very, very few are used in smaller firms. It's just too expensive, it's too complicated. We tend to think of robots today as being kind of where computing was in the 1970s. You know, if you're a big firm, you could buy that mainframe and you could, hire the software engineer, you could write the custom codes. But with the advent of the personal computer, the GUI, the mouse, applications, a lot of things came together to make that technology widely available, to democratize it. And that's what we hope to help fuel here over this next decade. So that's what we're about. If I come back here in about 2 years, I'll tell you lots of great stories about the stuff that's happening in hand, but we're still pretty early on. So I'm happy to, answer any questions and tell you what we're up to. But today I'm going to talk more about the stuff I've been doing for the past 30 some odd years in this field of haptics. So this word haptic comes to us from the Greek, related to the sense of touch, but I really think of it as the perceptual system associated with interacting with the world through touch. Two main systems in the body, the skin, the cutaneous, as well as the muscles in the joints. Both of them replete with sensory information that feed the brain and help you form a notion of things like shape and dynamic properties like mass and compliance, surface properties like texture that I'll be talking about quite a bit today, and many other factors as well, and certainly are critical in dexterity. Here's some just, an assembly of images of things that are rich in haptics, right? Some things are just assessing the world, feeling things, others like the potter's wheel or swing on the button that involve manipulation as well. One of my favorite examples is just the key fob. I might have mine in my pocket. No, I left it when I came. You can reach your hand in your pocket and you can pull out that key fob and not the other stuff that's in there. And you can find the button without looking, and you can press it and know that you've done that, and all of this through touch alone. It's really quite a remarkable sense. So I work on haptic interfaces, so building technology that lets us exploit that system to interact with digital information. Much of my career had some really interesting control problems. It would have been great icon seminars. Like how do you simulate dynamic systems like this spring that we're showing here right now in a really veridical way. That's a feedback control problem, right? The way this works is a force torque sensor here knows how this person is pushing on it. And that information runs through a real-time model of virtual world, which then tells the mechanism how to move. Very much a feedback control system, and there's some really challenging control problems there. So I spent a lot of time working on those sorts of things. And that sort of technology led to not my technology in particular, but just real world examples would be things like a dental trainer. Over the years, though, haptics has really kind of exploded into a wide diversity of applications. A lot of things in gaming, like a lot of use of vibration. Obviously, you've got it in your phone. Force feedback and things like knobs. Mid-air haptics, which is kind of cool. And its use as in things like electronic braille. Just a quick connection into the work I'm doing today on dexterity. This is what we call DexNex, or our dexterity nexus testbed, bimanual anthropomorphic hands, couple of eyes on a head and a neck up there. And then you see Toby up here, operating the whole thing. And he is getting some haptic feedback through those massive gloves he's wearing, little pneumatic indenters in there that take information from the green fingertips and feed them back to him. And it's okay, it's not great, but that sort of information actually is quite important in helping transfer his dexterity to the robot, which really is the main way that the world is training robots and training up autonomous policies. So certainly a current and future area where haptics is extremely important is in transferring human dexterity to robots. But today's focus is going to be on something called surface haptics, something I've worked on pretty extensively in the last couple of decades. And the idea here is to take a physical surface, like that piece of glass on that touchscreen, and control what you feel on, right? So you all know that you can't actually feel the buttons on the keypad on your iPad. What if you could? What if you could feel the edges, feel the shape, feel the depression, feel the click? those are aspirational examples of what I mean by surface haptics. Actually doing it is another matter, and I'm going to tell you some stories today about actually trying to do it. So how do you do it? There's a lot of approaches that people have tried. This is the one that kind of works, is just make things vibrate. That's what the Taptic engine in the iPhone does. Electro-tactile is a real favorite. It is essentially delivering enough current through your tissue to cause nerves to fire, create active potentials. The problem here is it's really difficult to hit the mechanically receptive neurons and not the pain receptive neurons. So this one often doesn't work as well as we'd hope it would. And then there's things like the idea of morphing the shape of a surface, so actually changing the surface itself. The work that I'll be talking about today took its original inspiration from work that Margaret Minsky, you know that name, Minsky, her dad, Marvin Minsky, is really considered one of the 2 or 3 fathers of AI. She did her PhD in the media lab at MIT and worked with a lab mate of mine. I was over in mechanical engineering to build a force feedback joystick. It would only move in the plane, but she discovered that having forces acting in the plane gave people the perception of out of plane shape. He called it the virtual sandpaper system. Later on, the late Vincent Hayward and his student did a really rigorous study shown in these 3 panels. They had people move a device over a bump and asked, what shape do you feel? And people said, I feel a bump, as they should. But then they had people move that same device over a perfectly flat surface while applying to it the pattern of forces that one would experience going over a bump, right? So you have to push your way up the top of the bump and then you get pushed on the other side. You can play that pattern of forces. You ask people what do they perceive, and they robustly feel a bump. It would happen to you too. It's a super robust haptic illusion. In fact, so robust that if you move down a little bit to play that pattern of forces of a bump, you feel it. So we thought that was pretty cool. What if you could do that on a surface? Maybe even with the bare finger moving on a surface. Wouldn't that be a nice way to generate really useful haptic effects? Some people had tried this sort of thing by doing things like over here, taking a clear film on the top of the surface and just kind of tugging it around and dragging the finger with it. Not so elegant. None of these are super elegant. Or a little pad with some wire you can barely see that was pull the finger around. Or asymmetric vibrations that sort of just nudge your finger along one way or the other. We started thinking about this from the perspective of friction. The big force your finger experiences when you're sliding on a surface is friction. What if you can modulate it? And that's what you see happening here. So what you see is the finger moving across these black lines. And every time it hits one, it kind of gets stuck. And so the black lines are clearly sticky, right? They're not. The black lines are actually just printed out on a piece of paper that's underneath a sheet of glass. This finger's just on a sheet of glass. But down here is a strip of piezoelectric actuator that can force that glass into a pretty high frequency, about 30 kilohertz, ultrasonic vibration. It's a flexural vibration that causes the glass to be moving out of plane against the finger by only a couple of microns. But that's enough to disrupt the friction between the finger and the surface and make it more slippery. And then we can modulate that. Right, so you can actually make it slippery when the finger's between the black lines, and then sort of the native friction of glass when it's on the black line. And it creates a very robust haptic tactile effect, essentially a texture. Actually, we discovered there's a couple of ways that you can modulate friction. If you think about friction as being, a friction coefficient and a normal force, you can vary either one. And so what I just showed you was a variation of effectively the friction coefficient, but you could also modulate normal force. And you can do that by creating electrostatic attraction between your finger and a surface. I'll tell you more about that in a minute. But in terms of modulating the friction, as I just explained, the way this works is out of plane vibrations. And we eventually really understood the underlying mechanisms for that, which have a lot to do actually with air. So there's some air captured in there. When you start to vibrate at a rapid frequency, it sort of acts as a pump and creates a little bit of an air bearing for your finger. My postdoc, Dr. Mertlowski, who's now faculty at TU Delft, made these measurements of friction versus vibration amplitude for a variety of subjects. but the key thing is kind of summarized down here. So if you look at the maximum relative friction reduction in the blue bars, in every case, not every case, almost every case, it's like 80% or above. So you're getting essentially an order of magnitude reduction in friction. It's not a small effect, it's a really strong effect. It's quite lovely. Feels good too. And so you can do things like this with it. The problem is, takes a fair amount of energy. The mounting conditions for the piece of glass have to be just right. Very easy to take that energy and shuttle it off where you don't want it. And you can't really isolate the effect of the entire glass is vibrating. So there's some challenges. So the other approach to modulate the normal force ends up being, I think, the more interesting one. And so I forgot I'm going to turn up the volume here and hope it gets picked up there. So my student, Craig Schultz, who's now faculty at UIUC, built this system. And so what's going on here? It's a black background. What it is a black anodized sheet of aluminum. And he grounded the finger and he can inject some current from the aluminum up through the finger. And when there's current flowing, the friction increases. I'll think about that in a moment. But you see the finger kind of bouncing around as it slides, and that's because he's varying the current flow at that frequency. What's really fun about this technology is it's very, very high bandwidth. So here it's very annoying, I know, but there's a 1 kilohertz tone. But to be even more annoying, you can play that pump through it. Maybe you can hear the music. What's going on here? He's taking the music, encoding it as a current, and creating vibrations and spin. So there's an area that you can signature. Right? The skin of the finger is the speaker. Right? So you didn't really care that much about playing that part. I didn't. But what the bandwidth is really, really useful. And so what's going on here in a little more detail, and just a little more detail, I can go into a lot more detail, but it's not that much fun, is that we just have essentially a stack up of layers to which have both some resistive and capacitive properties. So down here we have an insulator that was the aluminum, and then there's some aluminum oxide that actually is a leaky insulator. Then there's air. When air ends up being super critical, then there's you. And your skin, the outer layer of your skin, the stratum corneum, is pretty resistive, and so it acts as a series impedance here. And so you have these sort of three series impedances: the aluminum oxide, the air gap, and the skin. And the way this works is that when you have some current flowing through it, you create these potential drops, and it's the one across the air gap that's critical, right? Because that creates a separation of charge across the air. You've got incomplete contact here between your rough skin and that rough surface. This is always true. This is why friction acts the way it does. And as you increase the normal force, you get more contact area and increase the friction. It's really pretty simple. So, and Craig established this very thoroughly. So that air gap is so crucial. And it turns out that the force you experience depends upon the area of contact, the dielectric constant of air is essentially that vacuum, and then it depends upon essentially the electric field strength you can establish across the air gap squared. So having more current or more voltage is helpful. And you can do cool things with it. This is like virtual sandpaper, and you might be able to hear it. It's pretty cool when you can feel the roughness through this technology, hear it, and in this case, see it when all those sensory channels kind of line up. It becomes pretty compelling. Or this is one of my favorite ones. He's able to create the feel of flicking the switch. Again, you can kind of hear it, but then he can involve that with the impulse response of ceramic or metal, and you hear these switches as if they were made out of those materials. So it's quite fun. And I'm going to do a little brief interlude here. There's a storyline here, but sometimes you have to break it. So here's a little branch. Friction modulation is fine. I talked about modulating for friction, normal force. Sometimes you actually want to push the finger around. Imagine you want the finger to follow the edge of something. If I'm following along an edge, I'm moving that way, and the edge is pushing on me normal, right? And so I want to have forces that are not aligned with the direction of my finger, the opposite direction of my finger, that means I kind of have to move the surface. And so we started thinking about, well, how do we move the surface? And one approach is that you oscillate it in plane. And then you synchronize those oscillations to changes in friction. So if I want to push the finger to the right here, I make it low friction when I'm moving that way and high friction when I'm moving this way. So that gives us sort of rectification effect. And so you can generate forces, you know where the finger is, you can modulate those forces, and then from there you can begin to do things like create potential wells. And so think of a double throat switch, you've got a couple of potential wells separated by a hill. It's just a pattern of forces. And here are data taken with a human finger on one of these devices. This is the force data averaged and integrated, and you see the potential well looks really nice. And here's the actual toggle switch, the work that Eric Chubb did for his master's quite a number of years ago. And you can just kind of see the finger kind of go pop, pop, pop. It was really quite a satisfying effect that your finger kind of drop into these potential wells on a perfectly flat surface. So that was fun. But that's not what I'm really here to talk about today. Well, I'll finish up a couple other little things. The problem with that device that I just showed is it was oscillating back and forth, 800 hertz. Very audible, very audible, and also kind of numbs your finger. But we just couldn't get it to go any faster. And so I asked another student, Joe Mullenbach, if he could push it higher. And so his first attempt was to, okay, let's use the electrostatics. A previous device buried friction with the ultrasonic vibration. Electrostatics, we can go faster, as I showed you in an earlier video with music. So let's use electrostatics and still use in-plane vibration. And Joe was not able to push it much higher in frequency. It was still at around a kilohertz. So quite annoying to listen to, but of course the finger really strong. And so we were really learning something interesting here about using these electrostatics. So you can see the finger, the waggling of the finger is completely involuntary. It's just being pushed back and forth. Finally, my PhD student Hang Zhu got things working fully in the ultrasonic regime. So this is a sheet of aluminum. He is in the middle, putting into a longitudinal resonance at around 30 kilohertz. And then we synchronize that with changes in friction, set them offset by about 10 hertz. And so you get a 10 hertz force acting on the finger. And you can see how strong it is. It's really quite something. So this was a fun little diversion from the main work that we were interested in doing. But the rest of this talk is going to be about this topic. Because all along, as we're working on these devices, given that they could change the friction on your finger really rapidly, it really felt like we should be able to take a textual jacket here, somehow just record it and play it back. Right? And I think how critical that could be, or how nice that could be. Like, you know, we're on Zoom right now. We take it for granted that we can record audio, play it back. We can record video, play it back. But it's critical. Like people on the other end don't mistake it for the real thing, but they get rich information from it. You just can't do that with almost anything. And certainly not with texture. And so maybe we can do that with this technology. So we're going to talk about texture a little bit. It is an important surface property, right? So things like fabrics, we assess them through their texture. Products, the way the product feels is a really, really critical aspect. It's important in health. I mean, it's just important in a variety of ways. But there's this kind of question of what is texture? Like, how does your brain, what cues is it paying attention to make those assessments here? That's a tricky question. We'll say a bit more about that. And then, you know, what I just asked is, can it be recorded? Can it be played back? And frankly, the technology that we had developed help us accomplish that. So this is the question that we set out to try to answer. I'll show you. We had a little startup along the way called Canvas, defunct. But we could do detents. So this is a piece of glass with images, and you could feel like a little click, click, click of detents. Just great. This really worked. Every time we tried to do things that involve texture, like film the state of beard, we did this with Gillette in one of their ad agencies. They like won an award at the big ad contest, but conference, but you know, you wanted to feel the shaving cream, feel the smooth face, and I didn't do it, but it just wasn't great. Baby cries. It was, the idea here was to convince young men to shave, and not leave that stubble, and so once you have your baby, that's when you should start shaving, according to Gillette. We could create so many textures. We created them in that example. Just didn't feel realistic at all. Bobby Klatsky is one of the icons of the field of haptics. She's a faculty in psychology at Carnegie Mellon. She's worked in this field for even longer than I have, and member of the National Academy of Science. And she visited we collaborated for many years, but she visited my lab a number of years ago, and we were feeling these devices. And she just looked at me and said, you know what? Glass always wins. What she meant is that she could feel the textures, but there was never any question whatsoever that your finger was on a piece of glass. And it's just like, we actually collaborate to this day and meet almost weekly, and very few weeks go by when I don't remind her about that statement, because it really influenced the direction of work in our lab. Like, how do we go beyond the glass always winning? All right, so let's talk about texture a little bit. So just a teeny bit of sort of the underlying, you know, kind of neuroscience of texture understanding. It begins with mechanoreceptors that are in your skin. This is a cross section of the so-called glabrous non-hairy skin you have in your fingertips. And there's four main types of mechanically responsive receptors, mechanoreceptors. There's Meissner corpuscles, which are right up very close to the surface of your skin. Merkel discs, which are also right up there pretty close. And then your Pacini corpuscles are down deep. And then retaining organs, you don't have very many of, and they're mainly actually near the nail bed. And I'll tell you a bit about what they do. If you imagine two-axis system like this, where the horizontal is time, going from short time scales to long time scales, and the vertical is space, going from short up to long. Basically, each of them lives in one quadrant. So the Meissner corpuscles are your fast and short length scale receptors, super important actually for modulating grip, very important dexterity. When you begin to get a little bit of slip between your skin and the surface, creates a very localized vibration that these guys pick up. Also very important in texture. Merkel's discs, short length scales, but they're really slow to respond. So when something is sort of statically poking into your skin and causing it to curve, they're telling you that. So feeling the edge of a button or something, that would be a Merkel disc. This is the workhorse of modern technology. The Pacinian corpuscles are your vibration detectors that let you know when your cell phone is vibrating in your pocket. They're deep down in your skin, and they have this broad receptive field. They listen to vibrations coming from a large area. But they're super sensitive vibrations. People tell me they probably evolved because of mosquitoes. Mosquito or fly lands on your arm, you want to spot it, and you don't really care that much exactly where it is. You just want to get there fast. So when your phone vibrates in your pocket, you can think of mosquito. And then there's Ruffini endings, which are your long length scales, your long time scales. They're mainly there for detecting skin stretch. So when you lift something and you kind of feel your skin pull, you assess the weight of it from that. You're getting that from Ruffini endings. So all of these in their way are going to contribute to any type of haptic and tactile perception, including texture. And you know, a question in the field, more in the neuroscience field, has been, you know, which ones are important and how are they important? How do they lead to an encoding? So in the early 90s, in the lab of Ken Johnson and Johns Hopkins, some really beautiful experiments were done. It was a neuroscience lab, and so they actually had monkeys that they would insert fine wire electrodes into their fingers, and they could listen to individual mechanoreceptors, the responsive individual nerve hooked up to some mechanoreceptors. They would take the stimulus surface that had embossed patterns on it and rub it across the skin and listen to the skin, listen to the nerves fire. And then they could assemble, they could assemble their data into what they call spatial event plots. So these plots, the top row are the actual surface patterns, which is just a bunch of dots. So really simple surfaces. And then this essay is the Merkel that's been slowly adapting. This is the Meisner, this is the Chenian. So 3 of the 4 that I talked about. Chenian is the one that's deep down. So they're not listening to that pattern, just paying attention to vibrations. But these are the 2 that are close to the surface, and they are definitely listening to that pattern. The way we know that is what are these things? These are raster plots. Each line, horizontal line, is just saying that an action potential occurred at this moment in time. And time is essentially the same as space because it's when you get a constant speed across the span. And then they'll take it, and so that's you do a recording on a line, and you take this thing and index it over sideways a little bit, and do another recording, another recording, another recording. And after lots of experiments, these plots emerge. And what they tell you is that the texture is somehow likely encoded in these guys. In fact, they went on to show that that pretty much just the Merkel discs, these are the slowly adapting ones. They don't respond to things happening very fast, so these are very local. That you can use these plots. You can essentially involved with a Gabor filter that has about a 1 millimeter length scale and integrate it all up and get a measure of how rough a surface should be. And it matches the human, not monkey, but human psychophysics. The great thing about humans, you can ask them how rough something is, and they'll give you an answer. And so these are plots of the perceived roughness in solid lines and spatial variation computed from the monkey data in the dashed lines. And boy, did they just match up beautifully. And it just seemed there in the early 90s, like, okay, this is it. We now understand texture. But then, in the lab of Lake Singer, University of Chicago, they eventually found back in the like 2013, this paper was published. That was not the full story. The particular textures that the Johnson lab had chosen, these dots, was a weird texture. You only find those in nature. When you use those, they can recreate the data. But when you use actual things like fabrics, when you do the same experiment, especially as the fabrics get finer, it just falls apart. It doesn't work. And a lot of the stuff that we care about resides in these finer length scales. But if you look at things in time, it's interesting. So these are again these spatial event plots, but these are the Fourier transforms of them. And you see there's some structure here in the previous domain that wasn't really obvious just looking at the spatial event plots. They went on to show that basically if you combine the data from all the receptors, you can make very, very good predictions of at least roughness. Maybe people use roughness a lot in neuroscience because human subjects are really good at reporting roughness, really robustly data across people. So this works pretty darn well. It also turned out that the main contributor was the temporal information, not the spatial information. So, and from the early 90s, we thought it was all about space. From 2013, they thought, oh, no, it's really mainly about time, at least for fine textures. And that was good news to me, because I had this spreadsheet last time, spatial capability, a good time capability. We can really modulate our waveforms. Try that. Okay, we can't do raised dots, we'll never do raised dots, so we should be able to do chiffon fabric and nylon fabric and things like that. And so we tried. And of course, the glass kept winning. And so I asked my PhD student, Roman Grigori, please just pull out all the stops, do everything you possibly can to try to recreate texture and with our device, make it perfect. And at least if it doesn't work, then we'll know it's something. Spoiler alert, it didn't work. But I'll tell you how it didn't work. So Roman built this incredibly complicated device. Quite the figure here, but it's a tribometer. It's a device that you can put your finger on a surface. It'll control the normal force. It'll control the speed as the finger swipes across the surface, swipes past your finger. We can measure use a laser Doppler vibrometer to measure vibrations induced in the skin. We have a high bandwidth piezo force sensor to measure the forces between the skin and the surface. And just a lovely, lovely instrument. You could do things like put a texture sample on one side of it, and then this 3M glass we use as an electroadhesive display. I showed you the anodized aluminum version earlier. This is similar, but it's also transparent, which is often kind of nice. And so we could control the friction forces on that. And so we could do all sorts of nice experiments. Here it is in action. The red dot on the side of the fingers from the laser Doppler vibrometer, measuring the skin vibrations. You move across the texture, measure it, and then play it back as you go across this glassy surface. Okay. And boy, did it work. I mean, he put a lot of energy into making this thing work, but I'm going to show you there's 4 columns here. The first 2 columns are trigonometry, that means the forces. And then the next 2 columns are vibrometry, that means the vibrations. And each of them has time domain data and frequency domain data for each of those textures, the big textures. You can't see the blue, that's the original texture. All you can really see is the red, which is the virtual playback. And the red is sitting right on top of the blue. In other words, he made it just really work. I mean, he could measure a texture and play it back just darn perfect. It was quite a feat. So, okay, this ought to work, especially for fine textures, things like leather, velveteen, denim, swimwear, very fine textures. It really ought to work. Really ought to work. It was a complete failure. The virtual textures, they just did not feel like their physical counterparts. It was really one of the most disappointing results of our micro. It was a disaster. It was worse than that, really. To begin, the virtual playbacks felt way less intense than the physical textures. So you had subjects who are really good at reporting intensity as well. It's actually an interesting thing that I learned from Bobby Klatsky is like, I can compare the intensity of that light source to the intensity of sound, the intensity of texture. People are really, really good at kind of giving you ratings, even at class center values. So we have the intensity, and you compare the real texture in the black playback in red, and we gave people a knob, like adjust the knob until intensities match. And what they would end up doing is they would increase the gain of the playback from at least double to sometimes up to 16. I mean, crazy amounts of additional gain just to match intensity. And it turned out that the amount of gain they needed was related to how rough a surface was. The rougher it was, the more gain they needed. So we were way off in intensity. But then you would, okay, we will adjust the intensity to where they match. And now ask, how close does it feel? And Roman did that with this experiment. Remember, you've got the surface that's being slid under the finger. He could take 3 different physical textures. 2 of them are the same, 1 of them is different. Actually, the one in the middle is always equal to one of the other 2, but we could swap 2 outliers, and so we have to report, was it the different one, the one, on this side or on this side? And you had people do that here and here at the data. So you're comparing 1 to 100% of the time you can get it right. So a big number is good. And you see the numbers are pretty big. People are good at this. It's not a hard experiment to do. Then he did this. He took the real texture and he put the playback of it on one side and the playback of a different texture on the other side. So you're not asking are they the same, you're just asking, can you tell the proper playback? And here are the results. And again, big numbers are good. Not a lot of big numbers then. As you get way out here, and these are sort of organized around roughness, when you get to where things are really different in roughness, it's okay. But when there's at all any similarity, people are terrible. So again, a complete disaster. So we could have just ended the whole line of research right there. But we didn't want to, stubborn. And so we asked ourselves, what's wrong? What's missing? We're playing back, what's happening at the surface of the skin beautifully, right? And yet things don't feel right. what are we missing? And we concluded that what we were probably missing was what's happening within the contact patch between the finger and the surface. Because we're varying the friction across the entire thing all at once. And that's not what happens when you move across an actual texture. There's interesting things happening within that contact patch. So he set out to see whether or not that was going to be correct. And so he built this, actually did this during COVID lockdown. So it's kind of a little bit ratty how it was built, but he still did it. And he built a pen array that you can put your finger on. You'll see the finger come in here in a while. And the whole idea was to do some experiments about what's happening inside the contact patch. And so in all the experiments I'll show you, what he did is he just vibrated these, all of them at exactly the same frequency, exactly the same amplitude, but he would vary the phasing. So if you watch that video one more time, let me go back. You'll see like when they start to move, they're all moving in phase. And then you can get some of them going out of phase, and you can vary the pattern of which ones are out of phase and then how much they're out of phase. And so that's what he was able to do with this. And what he found is really robustly is that their perceived roughness increased as pens got more out of phase with one another, and as you had more spatial dispersion, meaning that if you had like half of them out of phase with the other half, that felt rougher. But if you then had quarters and they're all out of phase, that felt even rougher. And then by the time each neighbor is out of phase with this neighbor, then it feels really right. So that's dispersion. And the effect was not small. The increase in perceived intensity was up to about 2.5 times. And then he was actually able to build a very simple model based on skin stretch. You know that some of these receptors talked about it's in skin stretch, and basically he figured you can do that. You can integrate it up over the contact patch. You can look at skin stretch, the rate of change of stretch, and I won't bore you with all the details, but it worked pretty well. In fact, if you take the rate of skin stretch, rate of change of skin stretch, and you integrate it across the entire contact patch, it can fit the data quite nicely. So we thought, okay, we're onto it. What we were missing with our technology was the incredible importance of having a spatial variation within the content. So brings me to the last part of this story, which is the work of Sylvia Tan, who completed her PhD in our lab about a month ago. I took Sylvia and said, Sylvia, give me spatial variation somehow. And she had to develop some new technology to do it. And so what she developed is what she calls VoxeLite. Favorite name. She's the name. So what is VoxeLite? It's a wearable. It is unfortunately, we just realized we just can't do this with a finger on a perfectly flat surface. Maybe some future civilization can, we can't. So what she did is she still used the technology of electroadhesion, the same way that we were varying friction. But instead of varying friction between the finger and the surface, she varied friction between each of a collection of what she called nubs, these little black dots you see here. Each one is individually addressable, and she can control the friction between it and the underlying surface. The actual design is a layered system. She developed the entire design and manufacturing process for this, where there's a conductive layer and then a rubber layer filled with carbon nanotubes that she dialed in to get just the right level of conductivity. And so that allowed her to generate this electroadhesive effect by applying a voltage to the system. And it turned out, and I won't bore you with all the details. We initially tried doing this with these little flat pucks, but the stiffness of the skin of the stratum corneum was just too much. It coupled all of them into the plane. It turned to be really critical to actually poke into the skin. And can't just touch sideways on the skin. And so that's why these things have a single hemispherical shape, so that when you turn up friction, they tilt, and the tilting causes it getting into the skin. This actually also works when you just move it across a texture. So these things end up being kind of tactily transparent. You can wear this thing, move it across different textures, and really feel the textures in a pretty vertical way. They felt pretty good. So we had sort of two ways of using this: one through electrode heat, and one just sort of passively. And this diagram is just showing that it's using electrode adhesion, the same as I showed you earlier in the talk. Here's a little video of the device. It's just cool. She, again, sort of developed the entire manufacturing process. And then here you can kind of see what happens. Well, first of all, it weighs less than a gram, so pretty lightweight. She can make the density pretty high to where these are millimeter scale, center to center. And then you can see, and the ones that are touching back here, you can see them wiggling back and forth. Now, this is really critical. I'll show you another slide on this, but as you vary the frequency of activation, you can measure the vibration of the skin, and it's always large, above what is necessary for someone to actually feel it. And here they're all moving in synchrony, which is not exciting, but then here's like a checkerboard pattern. They're moving away from one another. You can kind of see them moving against one another. And these things are really easy to feel. What I want to get to is this plot in the lower right, but let's take a look at the middle here first. We have both forces and vibrations, similar to what I showed you earlier. And you can see a very slowly changing force, 2 hertz, all the way to 774 hertz. So it's a very wide bandwidth device. And here are the amplitudes of those vibrations. And this green line is the psychophysical threshold. Anything above this, you can feel. And we're way above it, 20 dB above it. So these devices are really easy to feel. Here's some video where we're just activating one of them. And you see that it can be really nicely localized. This is, of course, looking through we had to find an invisible person and look through their finger. It was hard to find that, but I'll tell you more in a few minutes about how we did that. And this is data associated with that video I just showed you, which is that in the normal direction, there's a lot more motion on the one that we're activating than any of the others. So we're not really, the control is nicely localized. A little less so in the lateral direction, but still pretty good. So then you can do cool things, like you can create little patterns as the finger moves along. You can have the nubs are activated, you kind of move around clockwise, counterclockwise, move across, move up and down, and ask people, can you tell which is the right pattern? And people are really good at doing it. So that worked kind of nicely. She worked with Caroline, an undergraduate student, to look about line following earlier, talk about following an edge. Imagine if you could, follow a line on a map on an iPhone screen. You just can't do that with any existing haptic technology. And so we were curious whether having this distributed array would help in that regard. So they did an experiment where they compared a situation where here's the line you want to follow. When you go across it, you activate a nub, or when we just activate everything in synchrony, which is the more like the previous technology. And the difference was really quite stark. So here are these lines in different directions, and somebody doesn't know which direction it is. They have to find it and follow it, find it through feel and follow it through feel. And when you have that spatial information, they're really quite good at doing it. So the motions tend to follow the line. Whereas when you don't have that, you kind of have to do this hunting thing where you just keep sweeping back and forth across it and find it, but you never know the orientation. You have no orientation information, which is one of the really frustrating things about the prior technology. So this was a nice advance. But the title of my talk was for tactile realism, and that's really what we've been building up to, over well more than a decade of work in the lab on texture. And so now is it finally possible? No spoiler alert here. I'll show you how she did it. She did have to figure out how do you actually measure these systems. And so she had to build a sensor. I know a number of you in this room are familiar with the gel site technology. It's a way of building a tactile sensor where you've got a transparent elastic medium and then you have a reflective surface that actually touches the world. You introduce light from the inside, and you look at the reflections off that surface. And as it deforms, when it's touching the world, you can reconstruct the pattern. So she built something like that. Built she also had sort of technology as the instrument to measure a texture, right? And then she had the actual device worn by a human as the playback. And so she's comparing here, no human in this particular case, she's comparing the measurement to what she was able to play back, and just showing that, yeah, she's getting pretty good quality playback of what she measures. She can get the same sorts of motions, and you can actually, well, here's the instrument. So this is a soft, transparent material in here. There's this thin layer, which is on the inside, coated with microparticles to make it reflective, perspective, sorry, it's a diffuse reflection. And then you can press it against the surface and really see the shape of the surface come through nicely. So she used that, and actually had the camera looking either straight down or from the side for different views in order to see what the system is doing. And then, so here is recording, I guess, leather, and then here's the playback. And if you can tell that they're different, you're better at this than I am. I mean, they're very, very similar in pattern. So we're pretty excited. Like, okay, this is gonna work. And so then how do you do that? In our field, you always have to build complicated machines and do these psychological experiments. And so she built this system. So you're over here, you're wearing the device. So you previously reported some texture, you're wearing the device. This whole arm is just to measure at a very high rate where the finger is relative to the texture. And then here is an actual texture on the other side. You can put one index finger on the device, one on the actual surface, move around and compare. But a lot of other things going on. Everything was heated to the same temperature to remove thermal cues, and that being very discriminative. And then we're controlling the normal force on the finger. And so that's kind of the basic setup. So again, you start by asking how good are people doing this just with their bare fingers. So I've got two different textures in my two fingers. Am I good at telling them apart? Do I have a good texture set? Everything feels different enough with two different. And so that was our texture set. And obviously people were pretty good at it because of the fact that along that diagonal, in this case, well, high number is so good. In this case, the diagonal is where you want to see the high numbers. You want to see that 100% of the time when it's aluminum on the left, you say it's aluminum on the right. Or when those two are matched, you say yes. And so people are very good at that. And so now, sort of the money shots, and really pretty much the end of the talk is when you compare the actual texture versus the rendered texture, you see that finally people are pretty good at it. Actually felt very, very good. The playbacks were really quite impressive. You could also wear the device, but not activate it, just move it across the actual texture compared to the playback. And it was still not quite as good, but pretty good, meaning that the device, again, is tactily transparent, that you can wear it and still feel the roll through it. This was quite nice. She published the results late last year in Science Advances. It got picked up by a lot of media, and I can't tell you how many people have reached out to her wanting to employ the technology for accessibility and other sorts of reasons. Probably will never happen, but it was quite nice that we finally, after a very long road, kind of got to where we could do that. So that's the end of that talk. I just want to acknowledge the many wonderful students who have participated in this work. Collaborators, I mentioned Mike Westy, also Cynthia Hickveld, Texas A&M, Michael Peshkin, Cobot co-inventor, continues to be a great collaborator in this work, and our support has come from the National Science Foundation. So thanks very much for your attention. Any questions? Yeah.
Oh, thank you for the great talk. That was really interesting how
One thing I noticed in the beginning of the presentation is you showed kind of this teleoperation process, and I can absolutely see the practical applications of this where you're kind of translating the texture through that. Could you maybe speak on kind of the workflow or what it would look like to have a practical process of translating the texture of something as the robot is maybe sensing this somehow, and for the person to receive that information that normally they would not be able to sense through their fingers.
Yeah, okay. You're asking about a use case in teleoperation. Where maybe I'm trying to teach a robot how to do some dexterous activity, button a shirt or something like that. And where it may be very helpful to feel that texture. And how would this work? And the answer is it probably wouldn't very well. This technology was really designed before all the excitement around trained robots. This technology was designed imagining that the main use cases are ones where we are in a virtual environment. We're wanting to assess textures in that virtual environment. So we can actually put our fingers on the surface and move relative to that surface. Relative motion is really key in this technology. Without it, you don't get the friction effect. And so it was those sorts of use cases that we imagined. The use cases that people have been coming to us with have been primarily things like virtual toilet. I imagine that a lot of conference rooms will have a little, like an iPad outside, and if you do this, swipe your finger across that and read about what's happening, it would be pretty nice. So it's use cases where the finger can move relative to the surface that this was designed for. The robot training one, that's not usually going to be the case. Usually you get the robot, they're doing something and you're maybe wearing gloves or you've got some sort of teleoperation interface. And whatever you're wearing, it's fixed relative to you. Which then makes this technology kind of useless. And we could just, have little motors that are constantly rubbing them against your skin. It seems like maybe not a great way to do it. So for that use case, I think there's some other technologies that might be preferable. And I'll mention one of them in a second, but the real amazing thing about this technology, the subtitle was human resolution. It's getting spatial resolutions that are comparable to the spatial resolution of your sensory system, and temporal resolutions that are actually beyond that understanding. So she can cover the full sort of spatial temporal sensory capability of your. And think about it like with displays. I mean, I remember when the pixels were big enough that you knew they were pixels, right? And the refresh rates, we all can remember watching really old movies when the refresh rates were really low as well. So we take it for granted that we have the refresh rates and the pixel density that makes the images on the laptop look very vertical. And that's what she's accomplished here with the texture. For robots, it's questionable whether you need that, at least today. It's probably impossible to accomplish that. But you need it not to be sliding versus your skin. And so there's a wonderful technology that Craig Schultz, who did a lot of the early electroadhesive work, who's now faculty at UIUC, has developed, where it has an array of electroosmotic pumps that can pump fluid and raise little bubbles up against your skin. It's a very compact technology. It doesn't have the bandwidth here, it doesn't have the spatial density of this, but it's still pretty cool in terms of letting you feel what a robot feels. That's the direction I think it's more likely to be successful. Great question. Yes.
So the texture measurement, like etc.
Yeah.
I think that also in the normal direction, also the shear direction, also important.
Yes.
But also the rate at which you're applying to is also somewhat important. How would you control if you have somebody's doing your finger? How would you control the precise loading rate in the instrument?
That's a really good question. Her technology did that with power weights and dampers, right? So it was really controlled just by the passive dynamics of the system. And I think you're right to ask that question. When you have direction reversals, there's a transient that occurs that we're not really controlling for. To do that, and I've seen people do it, it's a process. Maybe we didn't have the stomach for it, but really building a force control feedback system that just regulates that force. On the other hand, when you're naturally exploring a texture, you're not controlling it. The normal force is varying quite a bit as well. So we chose this intermediate path. But that's one.
Yeah. Oh, thank you for the wonderful talk. So I'm curious about the haptic array part. Is it always true that the higher the resolution of the interactive pins, the higher the realism that human feels?
That's another wonderful question. And as far as we can tell, it is not always true that a higher resolution leads to more realism. There's a number of sort of interacting factors as your resolution gets higher. Typically, the ability of each of these things to poke into your skin gets lower. There also gets to be a little more coupling between them. This is not just this technology, but others that we've looked at as well. And so there does seem to typically be a sweet spot, if you will, which is slightly lower resolution than you might think, which is a good thing for engineering. It makes it a little easier to engineer. So her experiments were done with a 6x6 grid over the contact patch. Actually, she had only 32 channels of control, so she did a 6x6 grid and then removed the 4 corners. So it was 32 of these inventors. And that seemed to work pretty darn well. We built them that would go up to 8x8, and it wasn't worse, but it wasn't better either. And that's just anecdotal.
Thank you. I have a follow-up question. So I understand your research is about surface haptics. There's a surface that the skin moves against.
Yes.
So I'm thinking about, I know very little about haptics, but I'm thinking about the video games.
Yes.
You're hammering the wall, but
Yeah.
there's no surface.
Yes.
So is there a way to maybe wrap a person with some physical surface?
Yeah.
Yeah.
Well, so maybe, that sounds wild. Yeah, the haptics haptics is a really hard perceptual system to work with. Unlike sight and sound, which are distance sensors, it's very much contact, so it's very embodied. And so if you're trying to imagine being in a virtual environment and hammering the hammer and feeling all of that, to be honest, it's hard for me to imagine how it's even possible to do that unless you rely upon some degree of illusion. And so there's a tremendous amount of work in haptics having to do with trying to fool people. So the way you would do this in practice is you have a handheld device with a little inertial reaction motor you would hit, and then in VR, you would see the hammer stop when it hits the wall, and you can hear the sound of it, and you feel the little kickback, but your hand would keep going, right? And usually people claim that's good enough. I think they claim that because it's all they can do, and I don't know, I guess I feel like if you look in the visual literature, you see lots of work on visual illusions. How many of those are actually important in our display technology? Sure, there are any that are. We use the limitations of the sensory system, the spatial resolution, the temporal resolution, but we don't really try to fake it out. Same thing with sound. And whereas in haptics, we're still in this mode where we're trying to find these illusions and exploit them. And it leaves me a little cold. I would rather we had a system, maybe it's a robot, and it's grounded, so it can actually apply forces relative to ground, and you hold on to it and you hit that, and it stops you. Right? And actually, I spent early part of my career working on that type of problem, which is a hard control problem, because it involved very high feedback gains, and but the hardware ends up being very complicated, and from a practical standpoint, usually not used all that much. So it's just a really hard problem. You're asking a great question.
Thank you for sharing your insights.
Sure. Yes. Oh, I saw that one first when I came back to you.
So, I mean, all of the data that we get is getting the smoothest surface that is possible on the roughest surface that is possible. After you take a good amount of data, you can generate your own synthetic data as well. Right?
Yes.
You can train your model on you don't really have to train it in real life. You can generate synthetic data and train your model internally from that. Do you think getting all of that data and then playing it back to real life could solve this problem?
Yeah, that's a really great question, and it's certainly one that I've had to think about, here in the age of AI, like, wouldn't that just solve these problems? And I'd say the answer is no. If you can't provide. If you can't provide the proper stimulus, in this case, actual spatial distribution, spatial temporal distribution. If you can't do it, then you can throw all the data you want at it, but you still, at the end of the day, your action space is not capable of exciting the system in the proper way. Where that approach you just described is proving to be useful is, there's a whole lot of research on looking at texture when I'm holding on to a device. So imagine that I'm exploring the world through a probe. And now that's much easier because I can use that pen book to put accelerometer to collect data, and I can put it some fuses in it to vibrate. And now I can do exactly what you're saying, because I can move it across many different surfaces, use them to train a model, then I can generatively create textures that I can feel through a vibratory device in that action. And so that's something the work that Heather Culbertson at USC is doing. I think it's just a great idea.
So a lot of the work that seems to be done is mostly on microscopes.
Yes.
Like they're very high resolution.
Yes, they're the phobia.
But we can still feel a lot of textures on other parts of our skin, yes, at lower resolutions. So have you explored anything applying these technologies to other parts of the body in order to like, not exactly extract them, but mimic those sensations, with just a low resolution of your skin?
Yes, we have. And you're absolutely right. You do have low resolution elsewhere. That does simplify things. I think the general coding that we're seeing here is ends up still being important. So you don't get away from still needing some type of spatial threading. Then the question is sort of how do you have to effectuate it, and interesting question, but a different sort of setting. So here kind of using the direction versus the world to do the actuation, certainly that option when it's mounted to your body. So then you have to do things like do little linear resonant actuators and such. Professor John Rogers at Northwestern is doing work along those lines, like collaborate with us, building these arrays that sort of just stuck on the body and generate various stimuli. I would say it has not gotten to the point of realism by any stretch. Then again, what is realism on other parts of the body is not something that's been super well articulated either. But to the point.
Yes. So I really like your talk on and also the research on looking at tactile in analogous to visual sensation, like instead of like my question is actually a follow-up question with another question about like what you could increase the resolution of the tactile. My question is, like in visual or in video, there is a threshold that will increase the frame rate up to 21 frames per second, that things become closer to realistic. Is there a similar threshold in tactile?
Yeah, it's a great question. I don't know that anyone has actually asked that question. I mean, frankly, until this technology came along, I'm not sure that it would be easy to answer that question. So maybe you just described the experiment that we should do. We probably could do that. I think we could do that. Anecdotally, I would say that the one we got these results with is probably at the lower end, right at that pressure. If we reduce the spatial density much, and I'm taking spatial right now, if we reduce the spatial density much more, then we begin to compromise some of the realism. From a temporal standpoint, one thing I'll say is haptics is way faster than medical. So you really need to be able to go from about 10 hertz at the low end up to maybe 500 hertz to really capture textures. And that, again, I don't think anyone has really formally said, here's the threshold. That one's a tricky one because
because of the nature of textured surfaces, there's also stress involved. But it's pretty well accepted, that's kind of the two range you need to do. We could add in the spatial, what a great idea, thank you for sharing that.
Is there any question online and quantitative?
No.
Okay,
Good.
good. I guess, yeah, we can conclude here. This is what, this time on, icon, you see this figure again. How do you press all the, icon property, putting your prop, to make each together, yeah, projects.
Okay.
Maybe we can go to the first page, we can take a peek when we get to the.
No, I don't mind. I'll put it on the first page.
Yeah, first
Yeah,
page.
okay, you bet.